Hi, my name is Matthew O'Kelly. Today I'm presenting our paper, BayesRace, Learning to Race Autonomously Using Prior Experience. To motivate the problem, let's draw a comparison to the ways which professional racing drivers prepare for an event. We can summarize the driver's work as 3 steps. First, the drivers identify the best racing line to minimize their lap time in a simulator. Then they practice in the simulator repeatedly to produce both fast and consistent lap times. Finally, they move on to the real track and adapt to the real-world conditions. The steps taken by professional racing drivers can also be used to develop autonomous racing algorithms. In this setting, we first compute the optimal racing line, given a track profile. Then we design a motion planner and controller that will help follow this racing line closely. Finally, we must learn to compensate for the model mismatch that may occur between the simulation and the real vehicle dynamics. In summary, this framing gives us 3 objectives. First, we'd like to compute the racing line efficiently. Next, we would like to identify a vehicle model. Since modeling is hard at the limit of the vehicle's handling capability, we would like to reduce the effort necessary for system identification. Finally, we would like to design a predictive controller which tracks the racing line. The focus of this paper is on the last 2 objectives. In the past, MPC-based planning and control has found several applications in autonomous racing. Both hierarchical approaches which separate path planning from tracking and contouring approaches which solve tracking and path generation simultaneously have been proposed. MPC-based approaches require a model of the vehicle dynamics. Accurate models like the dynamic bicycle model are difficult to identify and tune. As a result, some authors have proposed approaches which learn to correct coarsely or poorly identified models through iterative experiments. In contrast to these works, our approach utilizes a closed-loop system ID approach to correct the residuals of a simpler extended kinematic model that doesn't require expensive initialization and is deployed in conjunction with an automatic raceline optimization method and a tracking MPC. We conduct experiments on 2 open-source simulators, Orca, which is a 1/43rd scale vehicle, and F1/10, which is a 1/10th scale vehicle. The simulators differ in the underlying physics of the dynamical models. In both cases, starting from an e-kinematic model and following the same learning procedure, we are able to learn the dynamics of the simulator efficiently. In the remaining slides, we will discuss and explain our approach while highlighting the results presented in the paper. With that background, let's look at the problem setup. Due to the COVID-19 pandemic, we conduct our experiments entirely in simulation. The vehicle dynamics are simulated using a dynamic bicycle model. The simulator provides sensor measurements which we use to observe the vehicle's response to control inputs. For the MPC design, we initialize the model with measurements of the distance from the center of gravity to the front and rear wheels of the vehicle, as well as the mass. Note that all of these values can be accurately obtained without ever driving the vehicle. Since this model does not represent the true dynamics, we intend to correct the model mismatch using Gaussian processes. In what follows, I will walk through our iterative learning approach. There are 3 steps. First, we learn GP models to predict the model mismatch. There are many options for modeling vehicle dynamics. 2 popular approaches are the kinematic and dynamic bicycle models. The kinematic model only requires the distance from the center of gravity of the vehicle to the front and rear wheels. However, it fails to capture the potential of the vehicle's tires to slip. In the racing setting, this is especially problematic as we anticipate operating near the limit where lateral tire forces are insufficient to prevent the vehicle from sliding. In particular, the lateral and angular accelerations of the vehicle are not modeled. Instead, our approach uses an extended kinematic model, which includes the angular and lateral components of the acceleration. But unlike the dynamic bicycle model, does not require the identification of tire force curves. Since we have discarded the influence of tire forces, there is a residual error between these 2 models. In lieu of performing time-consuming identification of the parameters in the more complex model, we instead learn a correction to the simpler extended kinematic model by measuring the system's response to control inputs and approximating the measured error with Gaussian processes. In order to do this, we generate a data set by driving the vehicle and collecting sensor measurements. The tracker environment used need not be the same as the actual racetrack which we deploy the vehicle to. Then we train the residual model on the error between the extended kinematic model's predictions and the actual data. Finally, we're able to deploy the corrected model to the real track using a model predictive controller. Thus, we move to our second step, designing the controller. The MPC uses the corrected model, which is a combination of the e-kinematic model and the GP correction. To reduce the computational complexity of real-time optimization, we approximate the GP models by their mean estimates. The job of the MPC controller is to track the racing line, which was computed offline and discussed in other work. In the cost function, the first term corresponds to the tracking of the racing line. The second captures the control effort, and the third, the slack and the relaxation of track boundary constraints. We first test this controller using the extended kinematic model without the GP correction. The figure on the left shows the trajectory driven by the system in black. We also show the deviation in predicted open loop trajectories used by the MPC in red from the true responses in green. The higher deviation between the red and green curves, the higher the model mismatch. On the right, we demonstrate the performance of the MPC with the GP correction term applied. In both figures, the time is marked along the track at 0.5 second intervals. This figure shows that by reducing the model mismatch with GPs, we can also reduce the lap times. On an 8-second lap, the time is reduced by about half a second. Next, we compare the corrected controller to the MPC, which uses the ground truth model parameters. We observe that the GP-corrected extended kinematic model enables the MPC to achieve 98% of the performance of the exact model as measured by lap time. However, as the distance the vehicle has traveled increases, the error compounds. Thus, the final step of our approach is to update the GP models with newly acquired data from the target environment. By combining offline data from the original track with new data specific to the deployed environment, we retrain the GP models and run the controller for another lap. This time, we managed to learn the dynamics of the simulator almost exactly. In addition to the Orca platform, we also perform experiments on the F1/10 simulator. Through these experiments, we validate the generalization of the approach. Despite the change in vehicle scale and dynamics, the same MPC parameters achieve similar performance improvements. In fact, we're able to decrease the lap time of the vehicle by over 3 seconds using our approach. In conclusion, we've demonstrated how simpler kinematic models can be augmented with learned residual physics components to drastically reduce the complexity of system identification and enables model predictive control for autonomous racing. You can try out our approaches at this GitHub link. In the future, we hope to regain access to our labs and conduct further experiments on real vehicles, while also exploring more efficient optimization solvers and alternative function approximators. Thank you for your time.